formation of molecular orbital, that is following the principle of linear combination of atomic orbitals. Now let's see, what do you mean by the linear combination of this? What is the meaning of linear combination? If suppose simple, we will say 2 and 3. The linear combination could be in number line. This is 0, this is 1, this is 2, this is 3. The linear combination could be two and then 2 next this 3, 1, 2 and 3. So that means linear combination could be addition, or this linear combination could also be three. From this way we are coming to 2. That means this linear combination could also be minus. So there are two possible linear combination. One is additive linear combination, another is subtractive linear combination. So keeping this point in mind, we will also consider that the wave function, this 2 could be added, so that we will get a wave with larger amplitude, means where amplitude would be added. This is called in phase combination, or results in the formation of a larger wave function, more possibility to accommodate the electron, and hence this is of more stability. This molecular orbital is of higher stability and lower energy than either of the atomic orbital. This is known as bonding atomic orbital, formed by in-phase combination of the waves. Just consider one C wave is there, another C wave of might be different amplitude or same amplitude moving towards the same direction, then which will result to a larger wave. On the other side, we could have the opposite symmetry. One wave is here, another wave is countering through this. Then we will have a resultant wave whose wave function will be subtractive, or psi A minus psi B. This is actually countering the bonding or countering the stability of the molecule. Such an orbital, molecular orbital formed, is called antibonding molecular orbital. This antibonding molecular orbital is of lower energy and is of higher energy and lower stability than either of the atomic orbitals. So actually what we are doing, this linear combination is telling that number of molecular orbitals formed is equal to the number of atomic orbitals that undergo the combination. That means if 2 atomic orbitals will undergo a combination, we will get a result of 2 molecular orbitals. Out of this 2 molecular orbital, one will be of lower energy, that is called the bonding molecular orbital. Another will be higher energy with respect to either of the atomic orbitals, that is called the antibonding molecular orbital. Now the wave function psi is representing the atomic orbital. So psi A is the atomic orbital of atom A and psi B is the atomic orbital of atom B. Then the bonding molecular orbital is represented as psi A plus psi B, and antibonding is represented as psi A minus psi B. Now energetically, how we are showing this one? If suppose this is our energy diagram for molecule A, for atom A and for atom B, and this is the linear combination of atomic orbital. This is the energy of this first orbital, and this is the energy of atom B, atomic orbital A, energy of atomic orbital of atom B, and this is for atom A. This 2 would form 2 molecular orbital, one with of lower energy and another of higher energy. Consequently, it's evident that the one that is of lower energy is more stable, and the higher energy one is of lower stability. This one is known as bonding molecular orbital, and this is known as anti-bonding molecular orbital, or represented by psi star. There is some point of difference between the bonding molecular orbital and the anti-bonding molecular orbital, as the first one is the bonding molecular orbital is formed by the additive effect of atomic orbital. What I said, that this is would be psi A plus psi B, while the anti-bonding molecular orbital is formed by the subtractive effect of atomic orbitals. So this one will be psi A minus psi B. It's obvious that then the electron density would increase in the region between the nuclei of bonded atom. So the bonding molecular orbital will be of a larger wave with larger amplitude. So it provides the greater electron density in the region around the nucleus, while this provides a poor electron density, or electron density decreases in the region between the nuclei of the bonded atoms. It is represented by, could be of sigma molecular orbital or pi molecular orbital, while this is sigma anti-bonding molecular orbital or sigma star, and pi star or pi anti-bonding molecular orbital. Now let's see what do you mean by sigma and pi molecular orbitals. In the sigma molecular orbital, we are having two types of molecular orbital in diatomic molecule. One is sigma, pi. We could have another also, that delta and others, but it is not in the concern, since we have to only study up till neon in our syllabus. So delta and all this will not come over here. It's only sigma and pi. The sigma molecular orbital is formed actually when the combination of two atomic orbitals take place on the nuclear line of axis, that is along the internuclear axis. So in this case, the molecular orbital formed is called the sigma molecular orbital. For example, combination of two s orbital results in the formation of two molecular orbitals as the sigma bonding and sigma anti-bonding molecular orbital. Combination of two pz atomic orbital will also result as, one will be sigma pz, another will be sigma star pz atomic orbital. On the other side, pi atomic orbitals means when combination of two atomic orbitals take place parallel to the nuclear line of axis, that is parallel to internuclear axis. This is called pi molecular orbital. For example, combination of two px and two py atomic orbitals, it will form 4 pi molecular orbital known as pi px, pi star px, pi py and pi star py, means 2 bonding and 2 anti-bonding molecular orbital. And the energy levels will also be shown after that atom beryllium. When we have the boron, that is the p orbital is being included, then we will see how that pi and sigma orbitals are being formed in when the p orbitals are involved. Now here the most important thing is another, that is called bond order. Before that, once the sigma and pi molecular orbitals are formed, the filling up of electrons in sigma and filling up of electrons in bonding and anti-bonding molecular orbitals do follow exactly the same way as that of the atomic orbitals. That is the Pauli's exclusion principle, Hund's rule and Aufbau principle. It means that in molecular orbital, the electrons are filled up with the lowest energy level first, lowest energy to higher energy. As per the Aufbau principle, in one molecular orbital only 2 electrons can be present maximum, same as the Pauli's exclusion principle, and this 2 will be of opposite spin. And the third one is, in case we have the molecular orbital of same energy, first the single would be filled, after that the pairing would take place. That is called the Hund's rule. So the filling up of electrons in molecular orbital will also be exactly same as that of atomic orbitals. And thereby we will define a term that is called the bond order. This bond order is equal to half into number of electrons in bonding molecular orbital minus number of electrons in antibonding molecular orbitals. The most important significance of this bond order is, if we have a positive bond order, it means a stable molecule is formed. In case a negative bond order is there, it means unstable molecule is formed. And a bond order 0 means no molecule is being formed, or the molecule is not existing, or the species exists only as the atomic state. The dissociation energy is directly proportional to bond order. That is, a molecule with higher bond order will be more stable than a molecule with lower bond order, and of course a molecule with higher bond order will have a greater dissociation energy. Now, if all the electrons in a molecule comprising the substances are paired, the substance is called diamagnetic. And if any unpaired electron is present, it is also called a paramagnetic. The bond order is inversely proportional to the bond length. As we discussed this all in the properties of covalent bonds, the higher will be the bond order, the shorter will be the bond length. Later on we will see all the discussions in bond order with the individual starting from hydrogen to neon, the species.